Welcome to the Lionhearted Academy. Today is our trigonometry lesson number 7, and in today's lesson we're going to talk about linear velocity, angular velocity. Alright, so let's talk about what is the linear velocity. Well, velocity is actually speed over time. Okay, if you remember from middle school, we had a very common equation used is distance equal to rate times time. I'm not sure if you remember that. Distance equal to rate times time. The rate here was actually velocity. Now velocity is actually has speed and direction in it, but we're going to talk about velocity as v. So linear velocity is the distance traveled over linear distance over a period of time. So in our general discussions we are still having discussions on the circles. So let's go ahead and take a look at a circle. Let's say if you're traveling on a circular path. Okay, let's say you're running in a circle, running around in a circle. Or if you're running on a circular track, okay, let's say you're starting from point A here, and then you're running to point B. So that distance traveled, okay, let me highlight that. The distance traveled from A to B is the arc of the circle, which is S. So let's say you're starting from point A and point B, you travel the distance of S in a certain time t. So your velocity, your linear velocity, is determined by your distance traveled, okay, or the arc length in this case, divided by time. So that means it's going to be S over t. So the simple equation is linear velocity v is going to be equal to S over t. So that's how simply how we can determine the velocity if you're running along a circular path. Now linear velocity actually doesn't matter what kind of path you travel, whether you're running a linear path, a circular path, a line along a straight path, a line path, linear path, or it doesn't matter, as long as you take the distance travel divided by the time you spend, then that is your linear velocity. So for example, if you travel this 100 meters in 10 seconds, then your speed would be 100 meters over 10 seconds would be 10 meters per second. So meters per second or feet per second or miles per hour, all those are units for velocity. Okay. Now what about angular velocity? What does that do? Now angular velocity measures how fast you are turning, how fast the angle is turning. So let's look at our example again. And so initially we started with this side, okay, compared to the circle here, O, with the center O here. This is our initial side, which is also a radius, and then this is the final side, the terminal side, okay. OB is the terminal side, which is also a radius. So this is the radius, this is the radius. So if you're standing from A and you're running towards B, your angle changed from 0 radian all the way to theta radian, from A to B. And how fast is that velocity? How fast is your angle changing? Okay, that's called the angular velocity. How fast you're generating the angle over time. So your angular velocity is equal to the degree measure of the angle. So measure of the angle and divided by time. Now the measure of the angle, it has to be in radian. Okay, we're not using degrees because degree is not a real number per se. What I meant is that when you measure in radian, we're measuring in real numbers. So the formula would be theta divided by t. And so what letter do we use to represent angular velocity? We use a Greek alphabet, omega. Greek alphabet is called omega. Omega. You probably heard of that from somewhere before, alpha and omega. Alpha is the first alphabet of the Greek alphabet, and the omega is the last alphabet, the last letter in the Greek alphabet. So omega equal to theta over t. So omega is used to represent the angular velocity. Okay. Now, omega is used to represent the angular velocity. Well, is there a relationship between the angular velocity and the linear velocity? Well, let's think about this. S remember, how do we use to measure radian? When we measure radian measured, we say each theta, the radian measure is S over R, right? S over R. So S, the arc length, is simply equal to R times theta. So if I know the radius of the circle, and then give me a moment. Okay, so as we were talking, the radian measure is theta equal to S over R, and the S is equal to R theta. So if you know the radius of the circle, and if you know the angle in radian measure, you can find the arc length. Right, so that's the relationship we're going to use to connect the velocity, linear velocity v, and the angular velocity omega. Right, so v is equal to S over t, which is R theta over t. Okay, and as you can see, the velocity is equal to R times theta over t, right? But what is theta over t? Well, just look up here. We can see that theta over t is omega. So that means velocity is equal to R omega. Okay, I wrote it like a W, but it's actually omega like that. I'm sorry. Okay, so v is equal to R omega. That means the linear velocity is equal to the angular velocity times the radius. So that's the relationship that we can have, and we can solve for angular velocity if we have v over R. So this equation will also allow us to say, okay, angular velocity is equal to linear velocity over radius. Alright, so you have to remember the angular velocity is expressed in radians, because theta over t is radians per second. Radians per second. So let's take a look at some examples. Okay, let's take a look at some examples. Let's say if the angular velocity of a body is 300 revolutions per minute. So let's say omega is equal to 300 revolutions per minute. What is the value of omega actually? So this is called angular velocity. So let's say a certain thing is turning at 300 revolutions per minute. Now it's RPM actually. If you are familiar with cars, RPM is revolutions per minute. So your engines turns around maybe at 500, 600, 900 RPMs at idle, and when you're driving is maybe turning at 1,000, 2,000, 3,000 RPMs. That's what it means, revolutions per minute. So what is the omega value in this case? Alright, so now let's go back to the formula. Omega equal to theta divided by t, right? So we have to figure out theta in terms of radian measured, then divide by the time. So here they tell us it's 300 revolutions per minute. Well, each revolution is what? Is 2 pi radian. So let's multiply by the conversion ratio, 2 pi radian over 1 revolution. Okay, each revolution is 2 pi radian. So let's figure that out. 300 times 2, okay, that will be 600 pi radian per the revolution cancel out here. So it's 600 pi radian. That means the omega angular velocity for this object is 600 pi radian per minute. So omega is equal to 600 pi radian per 1 minute. Okay. Radian actually is not that it actually has no units. Okay. Now let's look at another example here. All right. Let's say we have a bicycle wheel. Okay. Let's say we have a bicycle wheel here. I'm sure you're all familiar with how bicycle moves. Let's say the bicycle wheels is rotating at a radians per minute. Okay, a radians per minute. So that's the omega for this bicycle wheel. Alright. What's the linear velocity of the wheel if the diameter is 28 inches? So let's say the diameter across the wheel of the bicycle, the diameter across the wheel, okay, is 28 inches. D equal to 28 inches. Alright, what's the linear velocity? So at at any point on the circle, what's the linear velocity of the wheel? How fast is the wheel actually traveling at? So the velocity, linear velocity is equal to what? Okay, I don't have to put a vector sign yet. Okay, so go back to the relationship between linear velocity and omega, and then angular velocity. V equal to r omega. So in this case, we know the radius is 14 inches. Okay, it's half of the diameter. This is the diameter, 28 inches. The radius is half of it, and omega is 8 radians per minute. 8 radian per minute. So when you multiply together, the linear velocity will be 14 times 8, which is 112 inches per minute. Now notice the omega has no unit. Actually, it's radian per minute, but that radian, it doesn't really have a unit. So when we multiply 8 times 14 inches, it gives us 112 inches instead of 112 inches times radian like that. Now, radian doesn't really have a unit. It's a unitless measure. So that's how we go ahead and connect linear velocities and regular velocities. Okay. Alright, now let's go ahead and try something more challenging here. Let's say we have a small wheel and we have a bigger wheel. Okay, they're connected together by a belt. Alright, so the small turn wheel is connected to the large turn wheel by a belt. Alright, so let's say the large turn wheel has a radius of 8 inches. So this wheel has a radius of 8 inches, and the small wheel has a radius of 2 inches. Okay, it's 4 times so small, so 2 inches. Okay, and 8 inches. And they're driven together by a belt with the 2-inch wheel. So what is the angular velocity of the larger wheel? Okay, what is the angular velocity of the larger wheel? If the angular velocity of smaller wheel is 200 pi radians per minute. So let's say the radius velocity of the small wheel is 250 pi radians per minute. How do we find out the radius, the omega of the larger wheel? Okay, well, one thing, okay, let's go ahead and take a look at this. Let's say the small wheel is turning this way in the counterclockwise direction, so it's driving the belt it's driving the belt in the counterclockwise direction, and it's driving the larger wheel. Now the belt is traveling at a linear speed. There's a linear velocity for the belt. So what we want to do is the linear velocity across the belt should be constant. The linear velocity across the belt should be constant. And so what we can do is we can calculate what is the v, what is the linear velocity here coming out of the small wheel, and then that linear velocity is going to get transferred to the angular velocity of the large wheel. Okay, so v here is equal to r omega s. Okay, I wrote it like w, I'm sorry, omega s. So that will be 2 inches times omega, which is 250 pi per minute. So that will give us 500 pi inches per minute. Okay, so that is the linear velocity traveling across the belt. And when we get to the large wheel, the linear velocity, the linear velocity doesn't really change, but it will transfer to the different angular velocity because of different radius. So the velocity the linear velocity is the same. Linear velocity equal to the radius times the angular velocity of the large wheel. So what we can do is we can solve for that omega L by dividing both sides by r. So the linear velocity is 500 pi inches per minute. Divided by the radius happen to be 8 inches. So we're going to do 500 divided by 8. So that will turn out to be 62.5 radian per minute. Okay, the inches cancel out, so the unit is actually 62.5 radian per minute. So as you can see, the angular velocity is different. It's definitely different than 62.5 pi, excuse me, pi. I did 500 divided by 8, that's 62.5, and so still have the pi there, radian per minute. So as you can see, the angular velocity will be different. And so this is a very useful setup in mechanics and in different things, like especially like if you're pedaling in bicycles, because if you notice usually we pedal on the larger wheel, and there's a larger gear, and then it drives the smaller gear, and the smaller gear drives the wheel of the rear bicycle. So let's go ahead and take a look at that example. Let's just go ahead and try that. Alright, so this one last example here today. Alright, so let's say we have a small gear here and then large gear, and the small gear So what we are trying to do is we're looking at the bicycle setup. This is a very crude bicycle setup. Okay, the front is the front gear which you pedal. Okay, the rear is the rear gear which drives the wheel. So this is the pedal. Okay, that you step your foot on. All right. Now let's make up some numbers here. Let's say this has a 4-inch radius, and this one has a 2-inch radius. Okay, and we're driving this. Okay, let's say we're driving this at well, let's say 100, 200. Let's do 300 radius revolution per minute. Okay. Alright, let's say we're driving the large wheel 300 revolution per minute. That's probably really fast. Let's go ahead and go down to 100. 100 is probably more realistic. 100 revolution per minute. So you're not really racing on your bicycle. You're just pedaling. Alright, I forgot to give you the wheel, the diameter of the radius of the wheel. Alright, the radius of the wheel is also let's say it's 14 inches. Okay. Alright, so what we want to find is what is the linear velocity you're traveling at if you're pedaling at 100 revolution per minute. Alright, so first of all let's figure out what's the omega of this large gear. The omega of large gear is theta over t. So in this case would be 100 revolution. 100 revolution is 100. Each revolution is 2 pi. So it's 200 pi per minute. Okay. So this is 200 pi per minute. All right. But then we have to figure out if you're pedaling. So you're driving your belt, your chain at a certain linear velocity. What is that certain linear velocity at that chain? Linear velocity of the chain. So let's find out what's VC, the velocity of the chain. That is going to be R omega, right? R omega L, because you're driving it. So R is 4 inches, so it's going to be 4 inches times 200 pi per minute. So that will give us 800 pi inches per minute. So that is the linear speed that you're driving the chain with. Now that chain is driving the smaller gear, and the smaller gear is attached to the rear wheel, and is going to convert that velocity, that angular velocity, into the larger angular velocity here. Okay, so what we're going to do here is let's go ahead and calculate the angular velocity of the smaller gear. Okay, now angular velocity of smaller gear is the linear velocity over r. So in this case it's 800 pi inches per minute divided by 2 inches. So that will be 400. So it's turning at 400 pi, right? 400 pi per minute. So the angular velocity is 400 pi per minute. Now, because the small gear and the rear wheel is attached, so both of them have the same linear angular velocity. So this is also equal to the omega of the wheel. Okay, omega of the wheel. All right. So then, lastly, we have to figure out the velocity of the wheel. Okay. So the velocity of the wheel will be equal to r times omega, and r is 14 inches. and then this omega of the wheel is equal to this 400 pi per minute. So it's rotating at 400 pi per minute because it's attached to the small gear, and that's this small gear is rotating at that angular velocity. So we can go ahead and take this and multiply 14 by 400 pi, so we get about 5,600 pi per minute. Okay, inches per minute. Okay, inches per minute. Well, how fast is that? Let's consider that. So let's go ahead and see if we can convert that to miles per hour or feet. Let's see what happens. Okay, so now let's go and convert that to feet first. Okay, so 1 inch, 1 feet is 12 inches, so we multiply by this conversion ratio, so we'll have feet on top. And then each mile has 5,280 feet. So if we multiply by this conversion ratio, we will set it up into miles. And then we want to convert a minute to hours, so we have 60 minutes per 1 hour. Okay, so those are the conversion ratio we're going to be multiplied. After that, all the inches cancel out, the minute cancel out, feet cancel out, so we have left with mile per hour. So let's type in the calculator here to find out what we have. So after a little calculation, now we also use the real value of pi here, so this will came out to be about 16.65 miles per hour. So that's a pretty good rate if you're riding a bicycle. 16.65 miles per hour, that's pretty good. So this is one of the applications that we will be using, especially very useful in terms of calculating angular velocity and linear velocity and transfer them back and forth. Alright, so thank you for joining for our lesson today. Please leave any question and any comments in the comment section below. We'll continue our trigonometry lesson next time. Thank you.